So in this video, we're going to talk about orthogonality in Rn. This is 5.1. U and V are orthogonal if their dot product is equal to 0. So in a geometric sense, if we were in 2 or 3D, the word orthogonality means the same thing as perpendicular. So we're checking whether our vectors are perpendicular. More generally, we can check whether the dot product of the two vectors is equal to 0, and that works better in higher dimensions where we don't have the geometry available to us. So an orthogonal set then, let's write an example of what an orthogonal set would look like, and then we can think through the details. So let's take 3 vectors in R3. So this is an orthogonal set, and what that means is that each pair of different vectors in this set are orthogonal to one another. So if we just give these vectors names, let's say we call them v1, v2, v3, we can check that the dot product of v1 and v2 is equal to 0. So first 2 vectors are orthogonal. We can also check that the first and the third are orthogonal. So v1 dotted with v3 is equal to 0. Yep, that looks good. And then the third pair would be v2 and v3. So v2 dotted with v3 also equal to 0. Now, second idea that we need is the idea of what it means to normalize a vector. So when we say normalize a vector, what that means is find a unit vector in the same direction. So in other words, when you normalize a vector, you're not changing the direction of the vector, you're just scaling the length. So for example, let's normalize. So in order to normalize u, we would need to figure out the length of u. So we'll take the square root of, we'll just square each of these components, sum those up, we'd have 6. So length of u, root 6. And so to normalize our vector, we're going to take u and we're just going to divide it by its length. So we're going to go vector u divided by the length of u. Normally we just write 1 over the length out in front. So there's our 1 over root 6, and then times the vector u. So geometrically what's happening here is you'd be starting with some vector. Let's not necessarily make it u, let's just make it any vector v here. Say the length of this vector is 11 units. Then if you take 1/11th of that vector, what you're doing is you're just producing a unit vector, maybe looks like that, that's going in that same direction. Okay, and then from there we can define an orthonormal set. So an orthonormal set is an orthogonal set in which all vectors have length 1. So when we say orthonormal set, we mean all pairs of different vectors in that set are orthogonal, and we also mean that each of the vectors in that set has been normalized so that the length is 1. So just to do a quick example here, we could build on our orthogonal set that we had back over here, and we could just scale each of those vectors. So we could say if you took 1 over root 6 times 1, 2, 1, and 1 over root 2 times 1, 0, negative 1, and then similarly 1 over root 3, 1, negative 1, 1. So there we have an orthonormal set. And let's talk about why we care about these orthogonal or orthonormal vectors. So let's write down a fact and then draw some pictures based on that. So our fact is that any set of n non-zero orthogonal or orthonormal vectors, Rn, is a basis for Rn. So one thing that's important here is that the vectors in this set have to be non-zero, so none of them should be the 0 vector. The other thing that's important is this idea of n. So if we are in R3, let's say we're in a regular 3-dimensional space, if you've got a set of 3 non-zero orthogonal or orthonormal vectors, you know automatically that's going to be a basis for R3. If you were doing a problem in R4, you'd need 4 non-zero orthogonal or orthonormal vectors. So let's try to understand on an intuitive level why this would be true. Suppose you start off, let's say we're in R3 just to keep things geometric so we can do some visualization. Say we're in 3-dimensional space and we start off with just 2 vectors that are non-zero and that are orthogonal to one another. So in other words, we've got these vectors that are perpendicular. Their lengths don't necessarily have to be 1. So these guys are perpendicular to each other. Now suppose we found a third vector that was mutually perpendicular to both the other ones. And again, we don't care how long or short this vector is. So perpendicular to that guy, also perpendicular to that guy. Well, by the fact that they are perpendicular to one another and that none of them are 0, these vectors are linearly independent. So we've now got a situation where we've got 3 linearly independent vectors in R3. And if we think back to our fundamental theorem of invertible matrices, as soon as we know we've got the right number of vectors that are linearly dependent, when I say right number, I mean the number has to match the dimension of the space that we're in. So as soon as we've got enough of these linearly independent vectors, we know we've got a basis for that space. Let's find an orthonormal basis, and we'll actually give these vectors names. So U1, U2, U3. This is going to be a basis for R3, and we're going to have a few conditions mentioned here. So we want U1 to be parallel to the vector 2, 0, 1, and we want U2 to be parallel to 1, 3, negative 2. All right, so we're going to try to find an orthonormal basis for R3 where our first 2 vectors have to go in designated directions. So to solve this problem, first thing I would do is think about the direction of U3. Let's say U3 is parallel to 201. It's parallel to 201 crossed with 1, 3, negative 2. Because when you take the cross product of these 2 vectors, that's giving us a direction that's perpendicular to both of them. So that's how we can find our direction of U3. Okay, so let's do our cross product. First column here, just a placeholder, and we're going to do this little 2 by 2 determinant pattern all the way across here. So what that's telling us is that U3 is parallel to the following vector. Well, let's see what our cross product is. Negative 3, 5, 6. Okay, so now to give our answer, here's our orthonormal basis coming up. We're just going to scale each of these vectors. So we're going to go 1 over root 5. I'm going to write these guys as column vectors just because I find it easier to write them down that way. So 1 over root 5, 201. Length of the second one, root 14. So we're going to go 1 over root 14, 1, 3, negative 2. And then I'll write the third one down here. So we just need to square each of these components here. Sum those up, that comes up to 70, so our length is root 70. 1 over root 70 times the vector negative 3, 5, 6. So that's our third basis vector there. Okay, in fact, if we're being really careful here, what we've done at this point is we've built an orthonormal set. So we can check that 201 and 1, 3, negative 2 are orthogonal to one another. That was just by design in the question. And then we've built this third vector that was mutually orthogonal to the first 2 by using the cross product. And then we normalized our vectors. So we've got an orthonormal set. Great. The way that we specifically know that this is an orthonormal basis, that actually goes back to the fact that we've got at the top left of the screen. So if we've got 3 non-zero orthonormal vectors in 3-dimensional space, that implies that we've got an orthonormal basis for R3. All right, so now we're getting into the main theorem of what we can do with an orthogonal or orthonormal basis. Let's call this a theorem because this is really the main idea for this section. So let's say that you're given either an orthogonal or an orthonormal basis for Rn, let's say. We're able to take any vector w in Rn and we're going to be able to write it as a linear combination of these basis vectors. So this is going to look like w is equal to the projection onto v1 of w plus the projection onto v2 of w, and we're going to have n terms like this. So I'll say plus dot 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 projection onto Vn of W. And that would be true for any W, any vector W in Rn. So there's our theorem. Theorem gives us a super quick way of writing any vector as a linear combination of our basis vectors. And what this relies on is that we have either an orthogonal or orthonormal basis. So that part is super important. Let's draw a couple of pictures just illustrating this theorem, and then we'll do an example. First, just intuition behind the theorem. Imagine that we are in R2. Imagine that we've got two basis vectors, which are going to be orthogonal to one another. So not necessary that they are normalized here, but they just need to be perpendicular. And now imagine taking any vector W in R2. So let's say this is W. These guys are the basis vectors, so we'll call them V1 and V2. So what this is saying is that it's good enough just to project W onto your two basis vectors. So let's project onto V1 first. Remember, you just look at the shadow of W. So you'd say, okay, there it is. And then projecting W onto V2, light source shining perpendicular to V2. Think about the shadow of W. So those are our two projections. And remember, vectors can be shifted. So this projection that we're seeing over towards the left, you could shift it over here. And so sure enough, W really is just the sum of those two projections. So that works great when you have an orthogonal or orthonormal basis. Now the caution would be, this is not true if the basis is not orthogonal or orthonormal. So if it doesn't fall into one of those two categories, that you're not going to be able to do this. So let's imagine we've got a basis for our two, where maybe our two basis vectors are very far apart from being 90 degrees from one another. Let's say they've got just a tiny small angle between them. So here's V1, here's V2. Now imagine we take some vector W in R2. Let's say this is W. Okay, and let's see what happens when we project W onto these two basis vectors. So there's our projection of W onto V1. Same thing for V2. Now we need a direction that's perpendicular to V2, so maybe roughly something like that. Think about where that shadow is going to fall, something like that. Okay, now there's no way that these two vectors that we've just built are going to add up to W. That just does not work when our basis is not orthogonal. So really important here that you've got an orthogonal set of basis vectors. They can be normalized. It doesn't matter whether they're normalized, but really important that they are orthogonal. So let's say that we're given a basis B. We'll do this in R3. So we're told in the question that this is an orthogonal basis for R3. If you want to check, feel free. First couple vectors, dot to 0. First and last, dot to 0, and last two, dot to 0. So we're all good there. But in principle, you don't need to check. What we need to do is write the vector W, which we'll say is 509. Let's write it as a linear combination of the basis vectors. So all we need to do here is project W onto the various basis vectors. There was no notation defined here. If you want, you can write something like call the basis vectors V1, V2, V3. Just so we're defining our notation, that's always good to do. And then we'll project W onto each of these. So let's first calculate the projection onto V1 of W. So let's remember our projection formula. I'm going to dot the two vectors together. So the V1 gets dotted with the W. And then everything else is about the vector that you're projecting onto. So you got length squared of what you're projecting onto in the denominator, and then that's times the vector that you're projecting onto. So if we do V1 dotted with W, that's going to give us 41. Length squared of V1 is 18. So you can say 41 over 18 times V1, or you could say 41 over 18 times 114, either way. Let's do the same thing for the other two. So projection onto V2 of W. Calculate the dot product of W with V2, it's 5. Divide by the length squared of V2, that's 2, and that's times V2. Okay, and then similarly, projection onto V3 of W, we'll take our dot product, that looks like 1. Length squared of V3, 9, and that's multiplied by V3. So here we've got our linear combination. W is going to be 41 over 18 times V1 plus 5 halves V2 plus 1/9 of V3. So that was way faster than doing something like Gauss-Jordan elimination to find those coefficients there. So extremely fast process, and that's really the bottom line of why we care about an orthogonal basis. It's so easy to then write any vector in our space as a linear combination of basis vectors with really minimal algebra. Let's recall from section 3.5. We talked about the idea of a coordinate vector. So specifically, we said something like the coordinate vector of W with respect to some basis. Let's say our basis is called B. And the notation that we gave for that, we said, well, just write down whatever vector W you're trying to describe. Throw some square brackets around that, and then just subscript the name of the basis. And what this vector represents are your different coefficients. So just think of this coordinate vector as capturing the coefficients that you would have found from your linear combination that we just did above. Coefficients, so it'd be 41 over 18, 5 halves, and 1 over 9. So we're just saying if you want to express W in terms of the basis, think of it as going 41 over 18 multiples along the first vector plus 5 halves multiples along the second vector, and then go 1/9 of the way along the third vector, and that creates your W. Let's define an orthogonal matrix to be an n by n matrix, so a square matrix, whose columns form an orthonormal set. So I would be a little bit cautious about this definition. There's something quite tricky with this terminology that we're saying orthogonal matrix, and yet the columns are supposed to form an orthonormal set. So if we were creating a new definition today, I would say, a nice thing to call this matrix would be an orthonormal matrix, but just due to historical reasons, it's called an orthogonal matrix, but yet the columns have to be orthonormal. So let's take a look at a quick example here. Usually when we're talking about orthogonal matrices, we tend to call them Q. And to confirm that this matrix here is an orthogonal matrix, we're going to circle the columns of the matrix. And so we're thinking of these columns here as a set of vectors, and we want to confirm that this set is an orthonormal set. So we want to confirm that when we do the dot product of these guys, we get 0. Dot product of these guys gives us 0. And also dot product of this pair gives us 0. So that tells us we've got an orthogonal set. We need something more than that. We need each of these vectors to be normalized as well. So we need to make sure that this first column, if we were to calculate the length of that vector, that would be 1. So just go through square each of the components and sum them up. You'd have a half plus 0. So length squared of this vector is 1. Therefore, the length of this vector is 1. Similarly, length of this vector is 1, and length of that vector is 1. So when you have all those conditions satisfied, you can say that your matrix is orthogonal, which again is the same thing as saying the columns are an orthonormal set. So here's a fact that will let us quickly check whether a matrix is orthogonal. The fact says that a square matrix is orthogonal if and only if the following equation is true. Q transpose times Q equals I. So if we know this equation is true, then we know our matrix is orthogonal. And conversely, if we know that our matrix is orthogonal, then we know that this equation is true. So let's do a quick example to understand why Q transpose Q equals I really encodes the idea that the matrix is orthogonal. So here's that same matrix Q that we were looking at a minute ago, and let's confirm that it does satisfy the equation Q transpose Q equals I. So I would start with the more complicated side, just write out Q transpose Q. So our first row would now look like this, second row would now look like this, and then bottom row would look like that. So that's our Q transpose. Then we're just going to copy out Q. So let's see what happens when we multiply Q transpose with Q. Just ordinary matrix multiplication. Let's circle the rows of the first matrix and the columns of the second matrix. And because the first matrix here is Q transpose, when we say circle the rows of Q transpose, that's really like circling the columns of Q. So essentially what we're doing here is we're just taking dot products of the columns of Q with themselves. So let's see what happens as we do that. So as we work with our first row here, let's do the various dot products. First dot product is going to be half plus a half, which is 1. Second dot product is going to be 0, and third dot product is going to be 0. So we can already sort of see what's happening. We're getting a 1 here, and that's indicating that the length squared of that vector is 1. Because we're really just dotting this vector with itself, and when you dot a vector with itself, you're getting length squared of that vector. So this 1 says length squared of that vector is 1, which implies length of that vector is 1. So this is what's telling us that our vector is normalized. And then the zeros here are telling us that this vector here is orthogonal to both this vector and this vector. So the zeros are what are encoding the orthogonality condition, and the 1 is encoding the fact that the vectors are normalized. So in our second row, for example, we get the pattern 0, 1, 0. And in the bottom, we get 0, 0, 1. So the 1s on the diagonal say that our vectors are all normalized, and the zeros in the off-diagonal positions say that each vector is orthogonal to all of the other vectors. So that's why saying Q transpose Q equals I is exactly the right condition to say that the matrix Q is orthogonal. Let's let Q be an orthogonal matrix, and we're going to show that Q inverse is equal to Q transpose. Well, given the fact that Q is orthogonal, the one thing we know from our previous fact is that Q transpose times Q equals I. So saying this equation is true is equivalent to saying that Q is orthogonal. So we want to somehow manipulate this equation to figure out that Q inverse is going to equal Q transpose. So the quickest way to do this would be to multiply by Q inverse on the right. So let's hit each expression here on the right with the Q inverse. We'd have Q transpose Q inverse equals I Q inverse. And let's see if we can simplify. So for the left expression, the Q and the Q inverse just give us I. So in other words, we've got Q transpose on the left, and on the right, we've got I times Q inverse, which is Q inverse. So sure enough, Q transpose equals Q inverse. So this should be true for any orthogonal matrix, and this is actually an incredibly useful fact. So think about how hard it is to find inverses for some of the matrices that we've seen. Well, if you've got an orthogonal matrix, super easy to find the inverse of that matrix. It's just the transpose. So we'll record that as a fact. If Q is orthogonal, then Q inverse is equal to Q transpose. So let's let Q be an orthogonal matrix. We are going to show that Q inverse is also an orthogonal matrix. So let's think about what it means to show that any matrix, let's say M, is orthogonal. So just by the fact that we wrote down a few minutes ago, the equation that encodes that a matrix is orthogonal is that your matrix transpose times the matrix itself is equal to the identity matrix. So what we want to show is that if we take Q inverse and transpose it, and then multiply it by itself, Q inverse, we get the identity matrix. If we can show that this equation is true, then we have shown that Q inverse is an orthogonal matrix. Okay, and when you want to show that an equation is true, you want to start with the more complicated side. So we'll start with Q inverse transpose times Q inverse, and we want to do a little bit of algebra here and eventually conclude that this is equal to the identity matrix. And if we can do that, then we've shown that Q inverse is orthogonal. Okay, well, what we know about Q is that it's an orthogonal matrix. And based on the fact that we just saw, for an orthogonal matrix, Q inverse is the same thing as Q transpose. So that first matrix really looks like Q transpose transpose, and then that's being multiplied by Q inverse. If we take any matrix and we double transpose it, then we get back to the original matrix. So we got Q times Q inverse. And sure enough, that's equal to the identity matrix. So yes, we've done what we wanted to do, which is to show that Q inverse is orthogonal. So some of these facts that we're establishing here, the fact that Q inverse is orthogonal, the fact that Q inverse is equal to Q transpose, we're going to be using these at the end of this chapter when we talk about something called orthogonal diagonalization. So we're just setting up a few things for later. So last example for this video, we're just going to practice a bit more the definition of an orthogonal matrix. So we want to determine values of x, y, z so that the following matrix is orthogonal. And there may be more than one combination of values. So we'll just try to determine all the possible values. All right, so remember an orthogonal matrix has orthonormal columns. So the place I would start here is with figuring out the x value, because the first fact that we know is that the length of the vector half x is 1. Both of these columns here have length 1. So in particular, that should help us figure out the possible values of x. So let's just talk about the length of this vector. It's going to be the square root of the sum of the squares of the components. So we've got root 1/4 plus x squared is going to be 1. We can square both sides and say 1/4 plus x squared is going to be 1. In other words, x squared is 3/4. And that gives us a couple of possibilities for x. X can be either plus or minus root 3/4. And I'm just going to pass the root to the top and the bottom here. You could make this root 3 over root 4, and then when you write it like that, you realize, oh, maybe it's better just to call it root 3 over 2. So x can be either plus or minus root 3 over 2. All right, so let's store that fact away for the moment, and then let's look back at our matrix. So now we should use the fact that the columns are going to be orthogonal to one another. So let's call this fact 2, and we'll just have a general discussion here. So let's say if the first column is the vector AB, then there are two options for the second column, because that second column is going to have to be orthogonal to the first column. So the way we're going to get the second column is we're just going to swap the components, and we'll have to change one of the signs. So we could make it negative BA, or again, swap the components, but then change this sign. So you can just do a little double check here. If you take the dot product of AB with negative BA, yep, that's 0. So this is definitely an option for the second column. And you can also check that if you do the dot product of AB with B negative A, you get 0. So this is another option for the second column. If you prefer to think geometrically about this, this is just like saying, imagine this is our first column. There are a couple of vectors out there that are going to be orthogonal to that. So the negative BA and the B negative A. Okay, now the reason there are only specifically two options is that, remember, we are not free to scale these vectors. So we can't take a vector that's longer or shorter. So I'm going to erase this. We're not allowed to do that. And the reason is this matrix is orthogonal. So we are insisting that both of these columns here have length 1. All right, and so if we put these two facts together, we should be able to write out a complete list of options for what our matrix can look like. So I'll just call this solution, and there are going to be 4 options. So first option happens when x is positive root 3 over 2. So that first column looks like half root 3 over 2. And we've just said that to get the second column, think about swapping the components of the first column or the entries of the first column and just change one of the signs. So here we're going to swap, and we could change, say, the top sign, or again, sticking with that first column there, swap the entries. So I got root 3 over 2.5, change the bottom sign. So there are 2 options corresponding to the case where x is root 3 over 2, and there are going to be 2 more corresponding to the case where x is equal to negative root 3 over 2. So let's write those out, and then we'll have our complete list of possible matrices. So now our first column is half minus root 3 over 2. We are going to swap the entries, and we'll have to change one of the signs. So I'll change the top sign. That will make our columns orthogonal. Or, again, sticking with that first column being half minus root 3 over 2. Again, swap the entries and change one of the signs. So let's now change the bottom sign. Okay, now we have another possibility. So these are the 4 possible ways of completing that matrix to create an orthogonal matrix. Remember, an orthogonal matrix has to have columns that have length 1, and all those columns have to be orthogonal to one another. So let's just confirm that we've answered the question. Determine values of x, y, z so that the matrix is orthogonal. I think it's acceptable to give your answer in matrix form, because then it's just a little bit more clear that you have found a solution. So that was our video on orthogonality in Rn. We've talked about orthogonal and orthonormal sets of vectors, and we've also talked about orthogonal matrices. Thanks for watching.